Yeah, welcome everyone. This is we're zooming in from Rice University in Houston, Texas. And this is part of the fourth one of the Earthbird Seminar series. And just some background, a lot of us started thinking about with science, we really wanted to hear about the stories behind the science, or stories behind the scientists, and put a human side to scientists. And that's why we started this. We're interested in anything related to the Earth. That's why it's called Earthbird. Could be biology, ecology, geology, of course, planetary geology. And then the bird part is just to describe, we just wander all over the planet looking at interesting things. So that's Earthbird for you. So our guest today is Leif Karlstrom, and he's a professor at the University of Oregon. He's a volcanologist. Um, uh, there are many breeds of volcanologists. He in particular is focused a lot on the fluid dynamics or the physics of volcanoes or anything that flows, actually, not just volcanoes. And the other thing that's quite remarkable about Leif is that he's a very accomplished violinist, a professional violinist, and he's the violinist of the bluegrass country band Front Country. And somehow he manages to do both jobs well and juggle all those things at the same time. But we're really fortunate to have him here at this time. We're going to talk about magmas, and then we'll end with bringing his music in, mixing it in with listening to volcanoes and so forth. So yeah, Leif, thanks for coming. Maybe to start off with, because we have listeners who are not all scientists, can you tell us a little bit of what volcanologists do, and then your part as a fluid dynamicist, what do you do?
Sure. Yeah, well, thanks for having me. It's a treat. Yeah, I guess volcanology as a field is sort of like a mishmash of all different parts of earth science. Because to study volcanoes, you kind of have to touch on all kinds of things. So volcanoes, although there's like maybe a dozen or so erupting every day, there are things that are not active very often, maybe. They're episodic. So like if you want to study a volcanic eruption, you can't just go out and like look at a volcano erupting, with some exceptions, right? Actually, up until very recently, you could fly to Hawaii and you could go poke at some hot lava or something if you wanted to. But that's kind of unusual. And often, volcanologists are interested in studying, eruptions that might have happened long ago on Earth's past. And in fact, many of the most interesting eruptions, the things that cause mass extinctions and have big impacts, we've never seen anything like that. And so you have to kind of be clever and use all sorts of different techniques to learn about them. And so I guess volcanology, as maybe Cin-Ty alluded to, there's people who are essentially chemists. There's people who, like me, are interested in the sort of physics. There's geologists who are going out and mapping stuff, and they're all contributing different things, I guess. Some people, make a career out of like globe trotting around to all the active volcanoes, and that sounds like a fun job. I sort of wish I did that, but I don't.
And diving into them.
Yeah, you get to where they say, yeah, sort of like Marshmallow Man suits. But no, yeah. So I guess my background, I guess I should really say my background includes geology, because I was brought up my father's a geologist. So I guess couldn't help learning something of that. But in college,
and
I
he's
studied.
on.
Yeah, he's here.
On as attendee. I hope that's not pressure on you.
Yeah, well,
But yeah, you grew up with geology all around you, but as I understand, not all geologists, kids actually want to become geologists. It often turns them away. Did you continue on as a geologist all the way from a kid, or you went off doing something else and then how did you come back? I think you came back. So
I came back to the dark side or whatever. Yeah, I mean, it's sort of like, I guess I did both things. Oftentimes it seems like when people get the chance to leave home, they go as far away as possible. And so I kind of did that to some degree. Actually, I left and went as far away as I could geographically. I guess stuck with the science to some degree, but I studied physics and math. And then my mom's a musician, so that's where the music comes in. So in some sense, I'm not really doing anything creative with my life at all. Sort of just going into the family business. So I guess that's that. But did at one point when I was finishing up my undergrad, got an opportunity to do a summer internship with a fellow down at UC Berkeley named Michael Manga, who was, it was a great summer. And I had never really thought about geology in this way. It's essentially using physics to study geological processes. And that got me, really kind of excited about this. Still did not have any intent of going into that field, actually. And finished my summer with Michael, and it was great. We studied zigzag rifts on lava lakes, and we did some experiments in wax where we were creating little cracks and studying what controlled the geometry of these cracks. And I was spending my days in the basement of McCollum Hall there in Berkeley, and so finished that up, and that was great, and went back for I guess it was my senior year at University of Oregon. I did my undergraduate degree, and thought I would try physics as graduate school. So I applied to some physics programs, and I was dating a girl at the time who moved to the Bay Area. And so I was like, well, I'm going to apply to physics schools in the Bay Area. So I applied to Berkeley and Stanford and didn't get into either of them.
Did they think you were too much of a geologist?
Yeah, I don't know. I guess I wasn't as good a physicist as I should have been. But it's for the best, I suppose. I was going to move down there anyway. I was kind of into like rock climbing, and I had a friend who had a business washing windows of high-rise buildings, and he said he could get me a job. That sounded pretty fun, actually. So I was going to just do that. But I'd been in contact with Michael Manga and sort of told him the scoop. I was moving, I didn't get into these grad schools. I was sort of sad, maybe I'll try again next year. And Michael writes back and says, well, if you wanted to do, earth science graduate school, I can, you can work with me and come and, join my group here at UC Berkeley. And so I thought about it, and it seemed like a pretty good option, actually. So there we go. So I never really actually applied, and it was never a thing that I sort of planned to do. But as it turns out, it was totally the right move.
It looks like it. I think one of the neat things about geology for all the listeners is, I see a lot of students that they come in, undergrads taking math and physics, and then eventually some of them realize, well, I don't really like it so much. But if they discover geology, they find out, oh, there's such a huge world that I can apply to math and physics and make it meaningful. So yeah. Why don't we, you want to start talking about some of your research?
Sure.
You want to share some slides?
Yeah, I can do that. Yeah, Cin-Ty asked me to throw together a couple of slides, mostly as sort of maybe conversation starters.
Yeah, starters, yeah. And we'll see where it goes.
So this is going to be pretty informal, and there's a lot of stuff missing, but I guess what I did here was, I don't know, I guess often in talks, you're like talking about a particular, I don't know, a project or something, like you're giving a seminar or something like that, and there's a theme to it, and hard to say that there's much of a theme here. But actually, there sort of is. I picked sort of 3 different projects that are represented by 3 different papers that are on pretty different aspects of volcanology, or maybe you could think of it as magma transport. So volcano, I guess, people talk about lavas and magmas in terms of this range of stuff that either comes out on the Earth's surface or doesn't make to the Earth's surface. And so I study that whole spectrum of things. So let's see here. I'll just share this so you can see that. I don't know how do you want to do this, Cin-Ty? I mean, I can just sort of talk through them, or what?
Yeah, well, this is a good one to start with. So I think a lot of people don't realize that it's just in earth sciences. I mean, volcanology is a perfect example of just the vastly different length scales and time scales that we have to worry about, right? So the volcanic hazards are probably on the order of days to seconds and hours things, and then building the crust is more on the millions of years. And you work on all of these actually across this.
Yeah, I guess that's, I mean, in some way, I sometimes use this slide when I'm like giving a talk to in some attempt to tie together these different projects that on the face of it seem quite different, but are all kind of touching on different parts of this elephant,
And University of Oregon, I guess I can help plug your institution there. You guys have done a lot to build a volcanology program there, and a lot of different people and expertise. And where do you your whole all the people there cover all this, or is there a particular focus in terms of the timescales here?
That's a good question, really. I think it does span the whole range. Yeah, I mean, there's quite a large group, and it actually was, there's been a recent, I guess, bump. There's a recent hire of several folks, volcanologists, to build this sort of volcanology center. But really, like, that's a thing that University of Oregon has done. I think, Alan McBurney and folks like this.
Oh, right, yeah.
Pretty strong for a long time. And in fact, one of the oldest buildings on the campus is called the Volcanology Building. And it used to be a hospital. So there you go. But yeah, I guess there's people that study this whole range from, like we were talking about earlier, the whole range of approaches too. So chemistry to pure modeling to going out there and digging pits and looking at cinder cones and so forth.
Well, maybe we can start with the assembly of magmatic systems. I think your second slide was something about I think it was Yosemite Valley.
Sure.
Yeah. What does it look like deep down in the crust, the parts that we can't see, right? And how do the magmas get there, and what do they look like? Are they big, small, or
totally
fracture their way through, or diapers?
Yeah, I should have, there's another cartoon that I sometimes show, which is people draw sketches. And it seems, for whatever reason, it might be fun to talk about why illustrations are such a big part of earth science, cartoons, why people gravitate to that as a means of conveying stories and ideas and quantitative things. But people draw sketches based on sections that we have, like that sort of sample the whole crustal profile, like so I guess it's a section of the Earth's crust that was once, was once vertical, but now has been exhumed and sort of tilted. And so you have this crustal section. And so you get, sort of a direct sampling of what does the crust look like as you go, down through it. Of course, it's like long since cooled and crystallized. So this is sort of like a pretty puzzling thing to make sense of if you're interested in the processes or the physics of magma transport, because it's like, some time integrated picture of a system that was likely active for millions or tens of millions of years. So there's all kinds of stuff superimposed on each other here, and that's really best. I think one of the best illustrations of it is this map. It's like a geologic map of the of El Capitan in Yosemite, which, like, all these geologic maps are showing these different units, which I guess are distinguished on the basis of composition or structure or something, right?
They're all different magmas, right?
Yeah.
Yeah.
And so this is some sort of like cross section through some ancient magmatic system. And then it's up to us to figure out what it all means, I suppose. But that's, I think, what got me interested in this as sort of a probe of magmatic processes, is that you look at something like this and you see, first of all, I guess what jumps out at me is just the range of different blobs. Right? You have lots of different sizes of things. You have very, sort of linear features. You have these blobby features. And so from the sort of fluid mechanics side of things, you start to ask, well, like why would you get this range of sizes? Are there physical processes that we can point to that would help explain that? And that was sort of the basis of the study, what ended up being this paper.
These guys, Stock and Glasner, did they free climb this and map it, or what did they do?
Yeah,
the scale of this is amazing.
It's huge.
I don't know if everyone realizes that, but yeah, it's a huge rock face.
It's true. I guess I'm sort of a poor presenter here. Every picture should have a scale bar, shouldn't it?
Well, there may be a little free climber there. Well, there's trees.
It's like 1,000 meters tall, right? Roughly. So largest cliff in North America here. So it's pretty big. And this guy, Greg Stock, is the Yosemite Park geologist, and he's actually a rock climber. And when they were doing this mapping project, I remember there was like a post on some sort of rock climbing website where he was basically like, if you're climbing, El Capitan, take pictures of all the belays and send them to me.
Oh, wow.
That kind of thing. There was definitely a component of this mapping, which was like right on the face. Yeah, pretty cool.
Yeah, pretty impressive.
It really is. Yeah, I mean, just the scale of this is kind of mind-boggling, actually.
And have you climbed this?
Yeah, I have. Yeah, a couple of times.
Yeah. Okay. So did you were you thinking about this at the time you were climbing, or?
No, not at all.
That was before your geology days.
Yeah, it was.
Okay.
I had other things to worry about.
That's true. Yeah, you'll have to go back up again now or down.
Yeah, right. You could also go down. People rappel off the top pretty frequently. Yeah. Well, okay. So but I guess the motivating science thing here is what governs the size distribution of plutonic bodies. I guess we call them plutonic bodies as opposed to volcanic, because these things probably didn't erupt or something like that.
Yeah.
And so you see, if you were to squint your eyes at this map, I guess I would say that you see two classes of structures. One class of structures is linear, long stringy things, and the other class is like blobby, pretty roughly speaking. And so that was the thing that jumped out to me, and that's what we based this sort of paper on. So this is it. This is our paper in a nutshell, more or less. And so I did some sort of abstract sketching here too. I don't know. I mean, you're an illustrator, right? An artist, and so I guess what do you like when you're drawing sketches in a geological context? What's your motivation for it, or like what?
Of course, you want to convey difficult concepts to and make it simple for everyone to understand. And there's sometimes you want to be really realistic, like the previous figure you showed, and sometimes you got to do more schematic like this to get the idea of concepts across. So I like this.
Yeah.
What you
did. I so what these sketches are supposed to convey, I suppose, is these two classes of structures, right? That on the left are these sort of stringy things, and they're associated with a physical process. These dikes, they're like, I guess they're like hydrofractures, but filled with magma. And so they're cracks, that are cracking the rock and transporting magma through them. And they're thought to be, I guess, the quantum element of magma transport in some sense, right? Of crustal magma transport. These are thought to be maybe one of the primary elements that's responsible for getting magma from the mantle to the crust. And so that's a baseline sort of hypothesis that we're building on. I guess you have this sort of like logic, thing that you're trying to set up and telling a story. And the base one is that magma is transported primarily through dikes. And so that's going to be a sort of a theme through the whole system. Even at great depth where it's very hot, you can still crack very hot rocks. I guess that's like the silly putty analogy that it might be kind of mushy and warm, but you pull it and it cracks. So you can still make cracks. And so here we go. So here's cracks. And then the other side is the blobs. And those ones, I guess, at least to my mind, those are the much more interesting ones from the physical perspective, because I feel like we have a much less well-constrained picture of what creates these things. Like I can look at a dike and I can tell you a story about the physical processes. I could even write down some equations that predicts the, say, width of the dike as a function of its length, assuming it's a penny-shaped crack in a infinite elastic space. We have some baseline models. This other side, I don't think that's really true. So in some sense you have a lot more, I guess, creative license.
Certainly in the cartoons they get very creative.
Yeah. So I guess one of the things that we did in this paper, and maybe I don't have a figure for it, but we went out, and I guess I would say we, but it wasn't me. It was one of the co-authors, this guy Scott Patterson at USC, has spent a career actually going out and mapping these things, these plutons, all up and down the west coast of the US. So, and what he has done, his mapping basically allows us to put together, a database, I guess, of the sizes of these plutonic bodies that you see. And I guess the reason that we did that is that I guess no one had. We looked through the literature. I had this question of like, well, what governs the size distribution of plutonic bodies? You look through different papers and you try to find an answer, and it's not there. So like, well, I guess we could figure that out. We have the data, and so that's what we did. And so I guess what we found, and I don't have a figure to show it, but is that there's a broad range of sizes. Maybe this is the better figure to show it, because really it's the real system that, like, if you look at these blobby features, there's a huge range of sizes. And actually what we found is that there's sort of a power law size distribution of these things. There's a small number of very large ones, and superimposed on them often, right? This is sort of a sort of composite system. There's bodies that have smaller and smaller and smaller sizes. And once you get to the very smallest sizes, these sort of quanta of magma transport, there's many of them. And the idea is that if these things are built incrementally by these little dikes, they're going to get mixed together. They're going to heat up the crust. They're going to make it warm. And so that process of mixing, I guess, is sort of that bottom figure is sort of thinking about the processes that govern whether an intrusion is going to become a dike or is going to be mixed into one of these blobby features. So that bottom figure actually, I think, is sort of the meat of the paper in some sense, or at least the figure that I think is the most interesting or most important, but it's pretty opaque.
It's a pretty intense figure.
Yeah.
Well, your first, A and B, you have this temperature profile, and maybe say something about that, because I think that's where listeners can probably gain some intuition there.
Yeah.
One is hot and one is cold, it looks like, right?
I think that's right. Yeah. So I guess, but it's relative, right? Because one of them is sort of, maybe it's rather than hot and cold, I would say one of them is like normal, like a normal geotherm, where say the rocks are, getting hotter and hotter at some roughly linear rate as you go down beneath the Earth's surface. It's not quite linear because of radioactivity, etc., but it's nearly linear. And so that's what that sort of red dashed line is. We call that a geotherm. And the idea, I guess, is that you place these dikes, and so you can sort of draw a line from this kind of pink region over to the right onto the figure. And all those lines in there are supposed to represent intrusions that have come in and they've frozen and they've deposited their heat into the crust. And so as you do that, many generations of these things coming in, solidifying, depositing their heat, you're gradually heating up the crust. And it starts by, heating up the bottom. this DE number is sort of a ratio of time scales. It's a fluid, these non-dimensional numbers are fluid dynamics folks love these things.
The Deborah number.
The Deborah number, yeah.
When mountains flow, right? Something like that. It's really
yeah. It's got some weird origins. But
biblical origins.
Yeah, but I guess it's sort of a measure of elastic versus viscous behavior in a material. And so if it's less than 1, the material is going to behave viscously. If it's greater than 1, it's going to behave elastically. And so you expect everything above Deborah number equals 1 to only host dikes. These are cracks, elastic, brittle failure features, whereas Deborah number less than 1 is going to have fluid mixing that is accommodating the mass input. So then you go over to the one on the right, and this is at these are real simulations, I guess, right? So I didn't just make this stuff up. It comes from solving a partial differential equation. But that right figure is I guess 400,000 years later, and now we've emplaced a bunch of dikes, and they've heated up the crust all the way up to 10 kilometers. And so the idea there is that whole region below 10 kilometers is now kind of viscous with respect to the dike input. And so it's going to form these big plutons, and they're going to mix together viscously. And so that bottom figure is sort of maybe a more thorough and quantitative depiction of that process. That basically you have the Deborah number there on the bottom axis, and everything to the left of Deborah number equals 1 is viscously limited, meaning that it mixes and you get these plutonic bodies, and everything to the right is dikes. Yeah.
One of the interesting things when I went back to look at your paper, the outcomes of this is that obviously this is all time dependent as you start to add dikes and it heats up. So the whole state of say this is an arc, like the Sierras or the Andes, is changing. The thermal state is changing with time. And do arcs, I mean, they must essentially just keep on evolving. This must have big implications if you're a petrologist like me, for average depths of crystallization, where magma bodies pond, where they degas, which then leads to ore deposits and so forth. The propensity to erupt. You want to say anything about that? The evolution of arc? Do they ever reach a steady state, or they're always evolving?
Well, I guess the steady state with respect to what? I mean, I guess there's. I like one of the things I've been thinking about a lot recently is eruption cycles. With maybe analogy to earthquake cycles. That people think about earthquakes as like, let's take the San Andreas Fault or something like that. You have like these large scale structures that are pushing against each other, and they're stuck. They're frictionally locked, but there's a long-term forcing. So they have to continue to stick and slip, right? So there's these cycles of earthquakes. And so by analogy, cycles of eruptions are in an arc, right? Your subduction is more or less continuous. You're continuously generating magma, but it's not like you have a continuous stream of eruptions coming out the top, right?
That's right,
It's episodic. And so there's this kind of transfer function, if you like, between the melt generation in the mantle and the eruption rate at the top. And it's nonlinear. We know that the relationship between the eruption size and its frequency is a power law, much like earthquakes. There's a magnitude frequency relationship. So what controls that? I think something that controls that is this, right? What the rheological state of the crust is, which in turn implies that things like when's the next eruption going to happen, basically are determined by the geologic history of that particular arc. So a lot, people are worried about these kind of, this gets us to the shorter time scale stuff of magma transport, but I think it's all, a lot of it is controlled by the mechanical and thermal state of the substrate that magma is transporting through, which itself is evolving over a much longer time scale. So you might have a steady state, but it's all superimposed on an unsteady process.
Yeah. Well, it's very interesting. It's just telling us that young arcs and mature arcs are going to be very different in the magma transport processes.
Yeah.
Let's see. Well, it's 7:30, so I just want to make sure we get time to talk about your other things. You want to move on to
Sure.
your other slides, or we talk about acoustics, infrasound?
Yeah, totally. Gosh.
Let you decide which
Yeah.
which way to go.
Well, how about we? Yeah, I'll just move through in order.
Okay.
Yeah, and we'll maybe try to not get too caught up on this next stuff, but this is like, latest and greatest, so it's fun to talk
Okay.
about.
Yeah.
This is thinking about, we're kind of, I guess, maybe I'll go back here, right? So this is this like timeline, and we started implicitly thinking about millions of years, or tens of millions of years even. So we're on the way left here. Now I'm going to sort of move to like the 1 to hundreds of thousands of years. So we're kind of moving right. And so this is the Cascades arc. So this is like my backyard or whatever. If you want to ask questions about volcanism in the Cascades, it's a great place to do so, although it's quite complicated. But this place has been really well studied, basically. So we have great mapping of all the vents that have erupted, and I'm focusing in this study on eruptions that have happened in the last, say, 2 million years, or like the Quaternary. And so that figure on the left is a database, again, that someone other than myself spent all the blood, sweat, and tears collecting. But this is the positions of all of the volcanic vents that have erupted in the Quaternary and the Cascades. So there's a lot of them. Right? Like, if you've taken an airplane from, San Francisco to Seattle, for example, the first order feature that you see is this line of stratovolcanoes. Quite beautiful. These things like just kind of poke out of the clouds, and you can naturally start to ask questions about what sets the spacing of these things and so forth. But really, there's thousands, in fact, about 3,000 vents that have erupted in the Quaternary and Cascades. And so here they are. And so you can break them down by volume. So we used satellite-derived topography and developed a little technique to cut out, essentially, volcanoes from DEMs, digital elevation models. And so you can calculate the volumes of all the volcanoes that have erupted in the Quaternary. And so here they are, and you can break them down by the type. So there's cinder cones, monogenetic things, polygenetic things. So monogenetic meaning something that's erupted once, or polygenetic meaning something that's erupted many times. And then we also have some temporal information. So it's not great. They're broken down by epoch. So that's on the right here, is the breakdown of volumes by the age of the edifice. And so it's not a linear scale, right? So the Holocene is only 10,000 years. Whereas the whole time period is 2.6. Late Pleistocene, I forget what it is, 800,000, forget. But it's not linear. So, but that's what we have, and it still is quite interesting because you do see there's some time variation. So this was sort of a large kind of data synthesis exercise, because once we realized that this existed, we realized that a lot of other data existed too. And so all these sort of questions about like how are volcanoes connected to subsurface structures, like we're talking about in that previous paper, you could actually potentially, answer some of those in a modern active setting. And so what we did is we compiled, geophysical data, so seismic tomography, heat flow, strain rates derived from GPS, this sort of stuff, and we interpolated it all to these vents. First, we, just to ask, like, what is the relationship? Essentially, you're doing a mapping exercise, but you're doing it in 3D. And you're asking what are the correlations between different data sets. So that's this. This is my second very opaque figure. But this is sort of the results of that. And so the leftmost panel here is if you take all of the geophysical data and you sort of lay it on top of each other and you say, what are the correlations between data sets? This is what you get. So this is, and the red lines are the outline of where you have volcanoes. And so this is sort of, in some sense, telling you what the what the subsurface signatures associated with the surface expressions of volcanism are. And so warmer colors here are telling you that you have greater magmatic signatures, like lower seismic velocities, higher heat flow, things like this that are sort of, it's fuzzy picture looking at geophysical imaging. But you can kind of say that this is the direction in which, if there's magma down there, it's going to be hot, there's going to be fluid. And so there's going to have, we also get, there's gravity in here too. So all these things together give you some sort of picture, and you'd like to look for self-consistency. So we're not going to trust any one data set, but we're going to put 5 or 6 of them together. And so the hot spots there are basically telling you where you have, a pretty prominent upper crustal magma transport system in the modern Cascades. That second one to the right there is the density of vents on the surface. And so we take all the points, those little points from the previous slide, and we fit a Gaussian distribution to them. And so that's why they kind of bleed outside of the red lines. So we're turning the discrete points of the vents into some sort of continuous function. But those are really telling you what the surface expression of magnetism is. So hot spots there are telling you that there's a lot of vents with large volume. So the hot spot is Mount Shasta, it's huge volcano with a lot of cinder cones and surrounding things. Medicine Lake is the one to the right of it. So I think just those 2 figures alone are kind of a profound thing to stare at, because it's sort of telling you from the data, there's no models in here, right? So I'm not doing anything tricky or making any assumptions, but this is sort of what the data are telling you about what the Cascades magma transport system looks like and how it relates to volcanoes.
Those colors, you're calling them hotspots, you mean that that collection of geophysical parameters correlates the most there. Is that what you?
Sorry, yeah, I guess that's what I mean. So the hotspots, I guess, are the warmer colors, so the yellows.
The warmer colors, yeah. So there's always the question of like where the surface expression of volcanic activity in an arc segment, is that dominantly controlled by deep level processes down at sub moho? Must at some level be controlled by that, and then there must be shallow level processes superimposed on it. But that's just a broad statement.
Yeah.
You want to add more to that, and what did you find here in that sense?
Yeah, I mean, I guess I should say that we really decided to focus on the upper crust. So geophysical sort of imaging of, say, the 10 to 15 kilometers is the deepest that we're sort of probing here. So this is kind of like mid to upper crust. And so this question of how that extends down the lower crust into the mantle, I think, is like future work or whatever. But but certainly this sort of goes to that notion of this transfer function, that you have a continuous supply, more or less. If subduction is continuous, you're continuously generating melt in the mantle, and yet what you see at the surface is by no means continuous, and in fact it's highly segmented in space as well as in time, right? Like the North Cascades is all these little discrete centers, and then as you go south, of course you have the basin range extension, and there's other things, other factors, right? I said the Cascades is complicated, and it really is. So but this is kind of telling you, I think, giving you a template for testing models, I guess, is the idea.
Yeah.
So you could take the ideas from that first part of this and map them onto this and see what they tell you. We haven't done that yet. But.
Yeah, I remember long ago there were ideas that the space, the distribution of volcanoes are controlled all the way down at the slab interface level, and clearly you've shown that there's so many that this transfer function that is very complicated. This is where we have to go for the research.
I think so. Yeah. I mean, I think I've even tried to do this at various times, is try to classify the various approaches that people have taken to explaining volcano spacing, right? And you can think of explaining it from the bottom up, some sort of like instability in the melt source region.
Yeah.
You can do it from the top down by, say, putting volcanic loads or glaciers or stuff like that change the stress state in the crust, and you can do it from within by pressurizing magma chambers and having structural pathways of that promote focusing, etc. So I tend to think about it in those three categories, and maybe there's some of each going on, but helps me kind of make sense of it. Yeah.
Before we run out of time, let's talk about your Volcano listening project and
Totally. Yeah.
Real fast before you move on,
yeah.
There's a question about why you stop at 49 degrees north for the Cascadia arc. They were thinking that thought there was more recent volcanism further north.
Yeah, that's of course the U.S.-Canada border. And that's the extent of the USGS database.
Gotcha. Okay.
So yeah, good question though. Yeah, the arc does extend into Canada. Okay, cool. So yeah, so Cin-Ty, to transition to the music stuff, I'm actually going to do it in a scientific way. So going back to this thing, I guess maybe we'll do that. We're now going to jump all the way to the very right-hand side of this scale. So it takes maybe, take a breather, have a sip of water or whatever. And then we'll do that. So this came about from a project where we're trying to understand seismic signals at an active volcano at Kilauea. And I'll just show this movie. I won't talk about the paper or stuff too much. But I think it's a nice way of motivating why you might think about this in terms of sound. So this is a seismic record collected. So here's island of Hawaii. Here's Kilauea caldera. Here's where it used to be the volcano house. Before the 2018 eruption, there was a nice observation deck there. You could look out and see this lava lake that sort of collapsed. But anyway, this is what was going on for about 10 years prior to 2018. So there's this active lava lake. We call this, I guess, an open vent system. So it's sort of a static lava lake, but it's convecting very slowly. So that's why it maintains sort of an active surface. So hot stuff is rising and cool stuff is sinking, and sort of maintains some sort of equilibrium. It goes up and down a little bit. But this is like, one of the best instrumented volcanoes in the world. And so there's lots of sort of geophysical proxies for what's going on at depth. And so this is a seismometer, NPT. You can see the station on the map here on the left. And you can see these little spikes, and those are basically chunks of the crater wall falling off and hitting the crater. And when that happens, it disturbs the surface and causes bubbles to burst, so forth. You can see as this timeline is something's about to happen because the seismic record gives it away. And here you go. So big chunk of the crater wall falls off. And of course, all hell breaks loose at that point. Can't really see anything. But the seismic record is kind of profound, right? It's like this beautiful damped harmonic oscillator with a period of about 30 seconds. Okay, and so there have been, in that 10-year long period of open vent eruption, thousands of these events, many thousands of them, a couple a day, of little chunks of the wall rock of this crater falling off and hitting the surface. And the idea is that this is basically like an organ pipe or some sort of resonating structure, right? And so you're basically perturbing that system and causing it to oscillate and resonate. And so the motivation behind this project is that you could maybe use the characteristics of those resonant frequencies to learn something about the geometry of the resonator and the properties of the fluid within it. So both of those things are basically unknown for most volcano studies. Like, what is the geometry of a magma plumbing system? Well, we don't know. We call them spheres and cylinders and so forth. But that's out of ignorance, basically. And likewise, the magma itself is this really complicated fluid, right? It's got bubbles in it, it's got crystals in it. And you'd really like to know the distribution of those because bubble content, for example, governs eruption style. So even from a purely hazard standpoint, you'd really like to know what the composition, the bubble content of a given magma is, and that'll help you forecast things. So we made a model of this thing. And so this is, what you're looking at here is plots of pressure in the conduit, and this is a conduit connected to a crack. And so it's resonating, and you can see all kinds of really complicated wave motions. So you're looking at time on the x-axis and depth on the y-axis here at the top, and so the pressure waves are bouncing around, and it's like an organ pipe. And so we wrote a couple papers about this. But recently I thought it'd be fun to listen to this, and this kind of interfaces with this sort of volcano listening project thing, where I've sort of started to think about ways in which listening to data might, well, help talk about it from a sort of outreach or educational standpoint. And then maybe, you know, if you're lucky, it might help lead to discoveries too, that this is we're really good, and we're highly trained, in fact, to look at data. But your ears are really good at picking up patterns in noisy time series. It's sort of like an evolutionary thing, right? Like, you know, if there's a ball flying at your head, to like move out of the way. So that sort of motivates that maybe there's some things about hearing that lend itself to finding patterns in noisy data. So that is a segue then. I took an output of one of these simulations. And so this process of turning data into something that you can hear is called sonification. And it's a field, you know, unto itself, as it turns out. People study this. It's hugely rich. And that's, you know, we talk about more of that. I've kind of been taking a deep dive myself into this field recently. But here's two signals, like I'm showing frequency. Let's look at the waveforms first. So this is two waveforms from an output of a simulation here, where I'm basically simulating pressure in this conduit crack system, and I'm querying that pressure at two different locations, one of them inside the conduit and one of them inside of the crack. And if you have headphones, you should put them on, because in my experience, computer speakers are not that good. You should you'll be able to hear the difference even through computer speakers. But I guess what I was maybe the exercise to go through is, can you hear the difference? Because hearing the difference will tell you something about the different processes that are governing these two things. So I'll just play them first, and then maybe ask what you hear. Okay, so let's play. I don't know. I'm not sure which one is which. So let's okay, I'll play it. Maybe I'll play it 3 times, and then I'll do the other one. It's very short. Okay, that's 2. Okay, so that's 1. Okay, now I'm going to play the other one. So remember, this is the same simulation. So this is simulating a rock fall hitting the surface of this lava lake. It's causing some resonance in the structure over, you know, tens of minutes. I've sped it up by, you know, a factor of more than 10. Okay, so here we go. Okay, that's 1. Okay. So what, can you hear a difference, Cin-Ty, between those two?
I do. I hear a subtle difference.
Yeah.
Not sure how to describe it though. The difference.
The pitch is different. One of them sounds a little bit higher pitched than the other one.
Yeah. Okay. Yeah. I mean, so in some ways, right? Like, you have to develop a whole language in order to talk about these things. So that's like one of the first issues. Is like, how do you? Because like listening is like very experiential, right? And it's actually in some ways like it's hard to make it as objective.
Note that Patrick is a violist.
Oh yeah. Well, there you go. So it helps to have training, right? This is why musicians, you know, spend years taking like aural skills, like so that you can hear, you know, differences in intervals and chords and so on and so forth. Because it, just like anything else, you have to train your ears. But nonetheless, right? I think we can probably all hear the first one. I'll tell you what the differences are, and then we can listen to it again. So the first one was a point in the crack, and the crack is this sort of like very flexible, wobbly, compliant structure. and it's kind of large. And so it has a much richer sort of like lower frequency resonant mode. And the conduit's more like an organ pipe, and it doesn't have that low frequency content. So what you should listen for in that crack one, which is I'll play first, is more bass essentially. Okay, so here you go. Right, there it is. And that was the conduit. You also hear some, like a whole host of other things. And if we, if we looked at the frequency content now, which we can do in this program, Audacity is so cool. You see this, a huge range of frequencies here. And some of them actually don't last for very long, right? This high frequency stuff damps out pretty early. And that's actually one of the modes of the resonance of these Crackless waves. They're sort of interface waves that are generated in the crack fluid interface. And they damp out super quickly. And so that's one of the things, that we're writing the paper about is like, well, what governs these different wave modes? You can see in the conduit, so that's the top one. The high frequency stuff is it vanishes earlier than the lower frequency stuff. Whereas in the crack, the higher frequency stuff lasts a bit longer. And that's because those Crackless waves are generated in the crack. So anyway, so I guess, I think probably my guess is that most sort of like science people would prefer to see the graph, right? You'd like to, if you're looking at a specialist looking at this, like you'd prefer to see the frequency spectrum, right? Like you prefer to see the things.
Good to be able to hear it so that you can relate the visual frequency spectrum to something that you can, hear.
Right. But that's sort of what this is, right? So like this is maybe the more traditional view of here's the time domain is the top one and the frequency domain is the bottom one. Mm-hmm. Right? So here's all these modes. There's a huge rich like spectrum of modes that are present, that are all superimposed, these different types of waves and harmonics of those waves. And I guess that was, I got a question before we started, I guess Linda asked whether this was like a synthesizer. And this is a synthesizer. This is how you make a synthesizer, is by generating a wave like this. And in fact, I went through the exercise just for fun of making a synthesizer out of the volcano. So here it is. Yeah. So I mapped this onto, so I sampled that. So this is the output of the simulation. So I'm now going farther and farther from science and more into art, right? So now I can create music based on my simulation of Kilauea or whatever, right? It's purely aesthetic, right? So I just sampled it and turned it into MIDI, which is the music format. And you can then I just mapped that. I have a program that will map that MIDI onto the keyboard, right? So I'm just hitting keys on my keyboard, right? And I can change the octave, do all this fun stuff, and then you can be a real audio engineer and put all kinds of sorts of other things on there. But I guess the bottom line of this is that you can do this with any kind of data. And you can make choices about how to sonify it. In this case, it's oscillatory data, so you just speed it up until it's in the human audible band, right? Like the human audible band is sort of 3 orders of magnitude. I think the lowest pitch you can hear is like 20 hertz, I think. Highest is like 20,000, something like that.
20,000. That's if you got really good ears.
Maybe if you, yeah, probably I would not be there, but that's 3 orders of magnitude. That's actually pretty small. Right, like a typical earthquake, you have energy, like a teleseismic earthquake, right? You have like energy from hundreds of seconds to many hertz, right? Hundreds of hertz. So it's way broadband, and so you kind of have to. It's sort of limiting, right? Like human hearing is not quite as sensitive, and like an instrument or. To really capture all the details. So we have to play games. And that's why sonification is kind of a fun field, is you get to play with all the perceptual dimensions. Like there are different qualities to sound that you can map to different aspects of the data. And through that, you can then superimpose data sets, right? And you can have a whole polyphonic sort of, whatever orchestra or of all the, say the geophysical instruments at Kilauea. I could sonify them all together and then just listen to it. And if I do it in an intelligent way, maybe I can hear the magma transport.
Singing to you, I guess.
Yeah. Yeah, I gave the talk about the Halemaumau stuff at Columbia a while back, and there's a guy there who I work with on the sonification called Ben Holtzman, and he he's great, and he saw that talk and he's like, oh, like it's like you're bowing Halemaumau, right? Because you're sort of exciting this resonator. I thought that was a great analogy.
So do you, Leif has a website called the Volcano Listening Project that you can go in and learn more about his sonification.
Yeah, I'll type I'll type it into the chat if folks want to check it out. Yeah, this is like a, I hope something that I'll get to do a lot more of. We're exploring a whole range of different, let's see, send to, maybe I have to.
It's there, I see.
Oh, you see it? Okay,
yeah.
I think I maybe messed up. Anyway,
yeah,
there it is twice. Yeah, but there's a whole range of different stuff, and we do a lot of sort of the more aesthetic, like pure music side of things too, which is to ask, like, science aside, could you create meaningful art by, say, using the data from Kilauea as an inspiration for composition, say, or improvisation? So you don't have to have any clue what the, physics are involved, but maybe you could make some compelling art.
Oh, for sure.
Yeah.
No, I think you're on to something. We're also accustomed to visualize. We always talk about visualizing data. Well, our ears are very sensitive, as you say, and just a little training will be able to hear a lot of subtle things. So I don't know what you call that, but instead of visualization, what do you call it? Just sonification? Is that what you're calling it?
I think it is, yeah.
Okay, but that's yeah, I think there's a lot of future in that. Well, we're running out of time. It's been a great having you here, but at the very end, maybe do you have any wise words to say, or what are some of the, we always end with challenges. What were the biggest challenges, or what's one of the biggest challenges now, or in your career? Young people always seem to think us professors have it easy and got here and no problems, but in fact it's a long journey.
Yeah, I guess there's the challenge is always finding enough time to do the things that you want to do. But I guess there's also, you don't always have the space to do it. I think that's why research, it's not like you become an academic to make a lot of money or something like that. It's finding a space that allows you to be creative and pursue interests. And I do view science as a creative enterprise more than anything. And that's challenging, as with any creative enterprise, like you lose inspiration pretty easily. It's like a very fickle thing. So finding problems that you're interested in, I think is the key to it, at least for me.
Yeah, and even when you're you get to work as a creative in your creative pursuits, you still have to. Sometimes we still have to do, so to speak, the dishes, the dull, boring stuff to keep our operations going. It's the unfortunate reality, but we also have time to really think about new things. And I like you say science is a creative enterprise. And I like how you bring in the arts, and science is really no different than doing art, I think. It's about interpreting the world. So, well, I guess we'll end there, but the formal part, if there are any questions from the audience, we can just informally chat for a little bit. Haven't been paying attention to the chat.
We answered the one Q&A question already, but maybe other people have more.
Yeah, so if anyone has questions, feel free to ask. Right now we have Michael Laura, a grad student here, says, that was amazing, thank you. Michael Laura, I've been watching your Facebook, Michael, or your Twitter, I don't know which one it is, but he's been mixing some interesting music. So he probably doesn't know that I know that, but yeah, fascinating, really fascinating stuff.
Yeah, I can if we just because I have it, I might as well play one more thing.
Yeah, go for it.
You know, this is the.
That's what I was going to ask. Play that. Showed us before we started.
Yeah, cool. Right, this one. Yeah, so this is this one actually we've spent quite a bit of time on and just got a paper accepted on it. So developing some new sonification algorithms, kind of this time thinking about how do you sort of deal with multiple data streams, I guess, and make sense of it in a meaningful way. And so this was a data set from a geyser in Yellowstone National Park. That I was actually part of the collection of this data when I was in grad school. But we took this data, and it consists of an infrared sensor that's pointed at the geyser cone. This is the Lone Star geyser that erupts like very regularly, like every 3 hours, and has since 1920, at least. So infrared sensor that basically tells you when hot water is coming out, and then a tilt meter. So just like at magmatic volcanoes, like a little tilt meter on the ground, and then a broadband seismometer. So 3 different types of data. And we want to listen to those data. And then to go along with the listening, actually, we found that it really helps to have a visual. So we animate them as well. And we use a sort of quantitative approach to animation as well, where you're taking the data set itself to drive the animation. Okay, so here it is. And we have, I guess these aren't public yet, but this is part of this paper. It's actually in the Computer Music Journal, so kind of a funny non-standard venue for a scientist. But this is so this is 3 eruption cycles. And they're 3 hours apart in reality, but we sped them up, so this whole thing will take 1 minute. And you can listen to all 3 data sets, and then there's an animation of them. Okay, so here you go. Oops. What's that?
The broadband is sonified. Is that what's going on here?
Yeah, so yeah, I can, maybe the key actually, we have a video that explains the sonification too, but I'll just describe it. So the broadband is directly sonified, so you just speed it up. So that's you hear that as the shh, the kind of noise, the noisy thing. And actually we're looking at the polarization of seismic ground motion. So it's actually taking advantage of the left-right stereo in your headphones if you're listening to it on headphones. And so you can actually hear particle motion going from right to left. So that's actually tracking bubbles in the subsurface. The low frequency kind of like woo kind of thing is the tilt meter. And we're animating that here with a MOGI model. That's basically measuring the deformation of the ground associated with water coming in and out of some sort of bubble trap or reservoir, much like a magma chamber. And then the high-pitched stuff is the infrared sensor. And we use a technique called granular synthesis, which is a little bit more of actually both that and the tilt meter use, I guess, maybe a more sophisticated sonification approach where you're mapping different aspects of the data onto different perceptual dimensions and adding little grains and things like this. So we could talk about that, but so I'll just continue to play it. I guess the other thing I should note is that in this eruption cycle, there are 4 stages. One is the jetting of water. One is the sort of precursory activity that water is kind of like intermittently getting ejected from the vent. Then there's sort of a steam phase where it's relaxing, and then there's a quiet phase where it's refilling. So that was the goal of this effort, is can you identify those 4 phases of the eruption cycle this way? There you go.
Very nice. It sounded like it was playing the chromatic scale for some part of it.
Yeah, so we did choose a scale. We chose actually a diminished scale.
Oh, diminished scale, yeah.
It's the most symmetric of scales, right? It's a whole step and then a half step and then a whole step and then a half step and then a whole step. Yeah. So there's some aesthetic choices, right? But like that's very similar to choosing the size and color of a dot on a graph.
Yeah, that's I didn't realize the aesthetic scale, because it gives a certain feel to it. Yeah, very cool. Well, any other questions from the panel here? All right, well, thanks, Leif. Hope all is going well in Oregon. You got a kid?
You have a kid.
Yeah. Is that, I'm hearing the kid in the background, or is it?
Yeah. Yeah,
Okay.
Almost 2.
Wow, boy, that time flies. But well, I guess we'll let you get back to your kid. So
yeah.
Thanks so much, Leif, for all of this. It's really fascinating.
Yeah, thank you. No, thanks for the invitation. It's fun. I don't really get the chance to talk about this stuff, so it's nice to get the opportunity.
This is fun. I learned a lot, and it gave me a lot of ideas too. So
cool. I should say, actually, the goal, we're not quite at this stage yet, but the goal is to make tools, right?
That would be great, so that people like me who aren't building these algorithms can play.
Yeah, I mean, because clearly you can use this. The idea is that you can use it for all types of data, right? Like event data, like as well as time series.
Yeah, any time series. I mean, that it might. Well, I'm sure someone's thought of this, but taking the carbon isotope, oxygen isotopic records and sonifying it.
Yeah. No, actually, I thought I had this great idea, and turns out it was not original. And in particular, Ben Holtzman has been working on.
He's been doing that for I think a lot for educational purposes, right?
Yeah, and he teaches this class at Columbia and has now for a couple of years. I don't know if he's doing it this year, but it's cross-listed between the music department and the earth science department. And the whole goal of the class is you pick a data set and you sonify it and animate it from start to finish. And so people come up with all kinds of cool stuff. There's really some remarkable things that people have done. So it's just like scratching the surface. So
I think if there's any way that you can make it easier for people to visualize complex data or sonify complex data, after all, humans, we are interpreting the data, and you still need that human element. We have to bring it into our senses, whatever they are.
Yeah.
Next one will be feel, I guess, touch.
Totally. Yeah, for sure.
Or taste.
So I think from that same point alone, this is like a really powerful thing. I've yet to find a place where I really feel like I've learned something new. Like, you know, the utility for actual research. I feel like the jury's still out.
Well, I mean, of course, you can write algorithms to recognize all the frequency bands, and you don't actually have to listen to it. But certainly listening, I think, will help people build that deeper intuition, right? And that's where I think it's more important.
Well, and I guess what I think still I'm holding out, because, you know, there's like more and more, especially when you get into active processes, you're just drowning in data.
Yeah.
Right. And so one of the hardest things is trying to make sense of all these data sets. And it's like, visually, it's actually quite challenging. And these people throw machine learning stuff at this, you know, and to great effect, but like, you're grasping at straws, trying to come up with ways to understand this really complex and just overwhelming volume of data. And so this is just another way, maybe.
There's a little bit of maybe purists like me, having machine learning do it all for you takes a little bit out of the fun out of it. Like, if you could listen to your data set and you can figure it out yourself with your own artificial into your brain, it's something really rewarding, right? That you I know this resonant frequency, or these triple frequency bands, things like that, which of course machine learning will figure out for you. But doing it on your own is something that's special. It's like I guess we got Fun Ling Liu here as a seismologist, and picking seismograms. Of course, there's so advanced now, it's automated, but doing it sometimes just on your own by hand, there's something special about that feeling to find it, see it yourself, I think. So
Totally.
yeah.
The
Okay.
analog approach.
The analog.
There was one more follow-up Q&A.
Is there one?
Sinan wanted to know, what would you call a new genre of magma-generated music?
Oh, yeah, I don't know. Gosh.
Magma pop or magma rock?
Magma rock.
You know, I tend to shy away from genres in my music making and listening. So I don't want to speculate. I'll let people come up with their own.
We didn't really get that much of a chance to talk about your other interests, your music interests, but maybe that we can save that for another interview.
Yeah.
Yeah, magma generated music. Any other? There's on the chats? No, that's all. Yeah, everyone's saying great stuff. So, yeah, thanks a lot.
Cool. Yeah, thank you. All right.
I guess we'll see you all later.
See you all later.
Bye. Well, that's it.